Hello everyone, welcome to COMP251 Data Structures and Algorithms. In this video, we are going to continue our discussion about recursion. In the previous video, we have seen an introduction to recursion. Recursive is a problem-solving technique when you actually, sometimes the problem is hard to be solved on its own. So it might be actually easier to find some way to use the solution for a problem of the same type but a smaller size, and using the answer for that smaller size, finding the solution for the original problem. So if you can find such a recursive relation, you can use a recursive algorithm to solve your problem. So the idea of the recursion is that you make your problem smaller, 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 and smaller until you reach to a small size that you know the answer for that. So because you know the answer for that, you actually just return that answer, and using that, the answer for the smallest size of the problem that you know it, that's going to be called the base of the recursion. So using the base and a recursive relation, you can solve problems of any size, right? So this is the idea of recursion. We have seen many examples in the previous video. So just a recap of our discussion that we had at the end of the previous video. Many problems can be solved either as a recursive way or in an iterative way, which is going to be non-recursive. So which one is going to be preferred? Is the recursive version going to be faster than the non-recursive versions? The answer is usually no, because when you write any function in recursive way, the computer needs to maintain the stack frames. So you are just actually putting some overhead to to calculate the, to create those stack frames and the releasing the, the space and all of those function calls. So the recursive approach is going to take more time actually. So is it going to take, in terms of the time, this is, this is different than those problems that we have seen for example, some recursive algorithms like the Fibonacci that we did actually a lot of repetition in the computation. That's a completely different actually issue. Even for those problems that the number of function calls is going to be equal to the the exact number of computation that we need to deal with the stack frames and function calls, so we are going to have some overhead. The recursive version of the non-recursive, the recursive version of the methods are going to be more time consuming than the non-recursive version. So the other question is the recursive version going to take less amount of space? Again, the answer is no, because of those stack frames. You have to actually keep copies of the, all those variables and a lot of the other actually information along with the stack frames, inside the stack frames. So no, the recursive versions, if you write a function in recursive version, definitely it's going to take more space than if you write it in a non-recursive way. So the next question that might actually come to mind is that, so why we care about recursion if that's going to take more space and more time to be executed? The thing is, recursion is a problem-solving technique. You should think about it as a way to approach the problem and solve, some complicated problems. The examples that we covered in this course usually, in the topic of the recursion, the examples that I'm talking in this lecture or the previous lecture are very simple examples, because I just wanted to give you the idea, just make sure that you get used to the idea of, this recursive thinking. In the higher level courses, you will see many problems like in COMP251, the design of algorithms. You will see many examples that you have a very complicated problem to solve, and if you just wanted to come up with an iterative approach to solve it, it would take a long time, or it's going to be very complicated. And recursion helps us to solve the problem. So it makes it much easier in terms of finding an algorithm to solve it. Then after you find the algorithm, you can switch and use an iterative approach, just convert your recursive approach to an iterative version. And not only that, in some cases, like when we are working on complicated structures like trees, writing a recursive function is going to be much easier and less error prone. So specifically in this course, when we talk about the trees, I'm going to show you a lot of methods that you can write in recursive way, and if you wanted to write them in a non-recursive way, the implementation is going to be much more complicated. So in those cases, we would definitely prefer to use the recursive way, and we can actually deal with that overhead of the time and space, and that's going to be okay because it makes the implementation much easier. Okay, so these are some examples from I have written these examples. I just repeat them from the previous lectures, so I'm going to skip them here. I think we have seen these examples in the previous slides. So the next topic that I would like to talk about in this video is about correctness of recursive relations, or the problems that you solve using recursion. The thing is, when you write a recursive method, you have to make sure that your method is correct. That recursive relation is correct, and it actually gives you the correct answer at the end. The way that we prove the correctness of recursion is based on induction, actually using the inductive approach from the discrete math. Basically, recursion and the induction are closely related to each other. You can see that in both of them we have a base, and for example, in induction, you just prove that assuming for example, the statement that you wanted to prove is correct for all the numbers less than or equal to k, you wanted to prove that it is also correct for a k plus 1. So you can see that this is kind of the statement k plus 1 is actually based on the proof of that is based on the correctness of the statement of size k or smaller than that. This is exactly similar to that recursive relation that we have, that when you are going to solve a problem of size k plus 1, you are going to use the solution of the problem of size k or smaller than that. So the proof that we do here is going to have two parts. We will actually basically prove that your the base case of your recursive function or method or relation, the algorithm that you wrote is correct, and then also actually prove that if the function is going to give you the correct answer for k, it will actually solve the problem for k plus 1 properly. Let me actually just apply this proof over the factorial. Again, because the problem is very simple, you might actually not find it very, interesting, or you actually just think that, okay, this is quite obvious, but because the problem is very simple. I just wanted to give you the idea that we have to prove the correctness of our recursive approach. This is just an example. Later on, when we see more complicated problems, definitely you will see the need of this proof, the correctness proof. So this is the definition of the factorial that we have seen before. There is a base case in this definition. You can see that the base case for factorial is n equal to 0. So for n equal to 0, when n is 0, 0 factorial is going to be 1, right? So this is the base case, and this is the recursive relation that we have. We have to actually prove both of them are correct. So as the base case, we wanted to actually show that, okay, 0 factorial, by definition, we know that it's going to be 1. If by looking at the definition of the method, we will see that, yes, this method for n equal to 0, this is properly going to return the value of 1, which is the correct value for the base case. The other part is the recursive part, that is saying that if factorial k is calculated properly, so factorial k, the method factorial k is going to give me really k factorial, the correct answer, I will properly calculate k plus 1 factorial. Okay, if I look at the definition of this method, it tells me that if you have this answer for n minus 1, so if you have the answer for k, this is going to be k factorial, it will be multiplied to k plus 1, right? This is going to be the answer. So if factorial, this function is going to properly calculate k factorial, this relation is going to properly calculate k plus 1 factorial for me, because k factorial is going to be k multiplied by k minus 1 multiplied by multiplied by 2 multiplied by 1, right? So, and then when you actually multiply this into k plus 1, this is going to be the definition of k plus 1 factorial. So this is enough to prove that, yes, the function properly calculate k factorial. It's actually clear here that we are talking about the positive numbers. So the function only works if the number that you pass is going to be non-negative. Otherwise, it's not going to actually work. Okay, so after actually talking about the correctness of the recursion, the thing is, I would like to discuss about the time complexity of recursive approaches. So far in the discussion that we had in the second week of the semester, we have talked about time complexity of methods, right? And we actually usually just calculate the time complexity based on this fact that we have seen, for example, some loops in the definition of the methods, and we usually actually just see the versions which are all the codes that we have already seen were iterative. So, analyzing the time complexity of recursive approaches are definitely more complicated than the iterative version, because some of the computations are not explicitly written when you look at a recursive method. Okay, so before I get into that discussion, I'm going to give you another example for recursion, and then I started talking about the time complexity over this example. Okay, just assume that I would like to write down a search function, a sequential search function, that we have an array of items, and we would like to check a specific value in the array and see that if this value exists in the array or not. So the input for us here is an element that we are looking for, an array of items, and we wanted to actually just search in that array of items, and I just assume that this is just a random set of items, so we don't know any previous information about this array. So basically the only thing that we can do is a sequential search. Okay, so this is the iterative approach that we wrote for it, right? You just write a loop that checks all the item in the array, compare them with this given item. This is actually this version that I wrote, just I assume that all the items are integer values. You can just write a generic approach of this as well. It's just up to you. I just wanted to simplify the version, the code that I'm discussing here. Okay, so you got an array of integers here and you have an item that you are looking for. Okay, so you look over all the items. You have a loop that goes over all the valid indexes of the array and compare each item with the given item. If it is equal to the given item, you return true. If you exhaust the loop and you did not return any, you did not actually finish the function here, you could not find the item, at the end you will just actually return false, right? Okay, what is the time complexity of this function? It is clear that you have a loop, right? And this loop, if the item is not in the loop, definitely it will iterate and go over all the items, and at the end it will actually reach here and return false. So it's going to iterate n times if you have n item in the list. Even if the item does exist in the array, if you randomly try a couple of items, you will see that on average, the number of comparisons, the number of times that the loop will iterate is going to be n divided by 2, okay? So this is just a discussion of some statistics. So on average, the number of times that you need to iterate to find the item, even if the item exists in the list, is going to be n divided by 2. Again, because it's going to be some value depending on n linearly, the result is that the time complexity of this function is going to be theta of n. It is going to be a linear search, right? Sometimes we call it a linear search or sequential search, so this is going to be linear. So I wanted to ask you to think about a recursive approach to solve the same problem. We have a sequence of items, okay? And we want to look for a specific item in this list. We don't know anything about the order of items here. And I want you to find a recursive recursive approach to solve the problem. So I cannot actually go with an explicit loop like this. So I would like you to you can pause the video, think about it for yourself, then come back and actually listen to the solution. Okay, so the recursive idea here is that I would like to find some way that I create a problem of the same type, which is going to be a problem of searching for an item, okay, but a smaller size. What is the size? What is the size of this problem related to this problem? The size is going to be the size of the array. Okay, so when I'm creating a problem of a smaller size, I should make the size of the array smaller. This is the way that you should approach to this type of problems to find a smaller, define a smaller sub-problem. So the recursive idea is that the item that I'm looking for, X, is going to have two options. I can actually start to think about it from the end of the array and say that, okay, either X is going to be the last item in the array, or it is going to be in the items from index 0 to index, for example, n minus 2, because if you have n items, this is going to be index n minus 1, and so this is going to be a problem. If this is going to be a sub array, right, of size n minus 1 from index 0 to index n minus 2. Okay, now you can see that this is exactly the recursive relation that I'm looking for. if x is equal to the last index, you found it. Okay, return true. If it is not equal to that, search for x in the subarray from index 0 to index n minus 2. Okay, this is going to be exactly a problem of the same type, but a smaller size, because I make the array smaller. I reduce the size of the array from n to n minus 1. This is exactly the idea of the recursion here. Either x is going to be in array index size minus 1, the last one, or it is going to be here. That for actually solving this one, what can I do is that calling the search over the same array but with a smaller size minus 1, so that it's just like you are reducing the last index and looking for the same actually argument. We are still looking for x. I'm not going to change that. The size of the problem that will be actually reduced is in fact here. Okay, so if x is equal to this one, you will to return true. If the x is available to an array of size minus 1, of size n minus 1, for example, again you return true. Otherwise you will return false. How to write this recursive approach? I can write it in this way. You can see that here, instead of actually creating a sub array, for example, if I have an array of size n, instead of creating another array of size n minus 1, what I'm doing in terms of actually just writing the code is that I would define another variable that is integer, and this one is just mentioning what is the size of the array. So in this way, I am just passing the original array, but changing the size of the array using a variable. This is important because this trick helps me to avoid recreating the arrays. This is definitely much better than creating an array of a smaller size, because when you are creating an array of a smaller size, you have to copy all these values, right? And this is going to take some time. So instead of creating a new array and passing a new array, which is going to take more time, what I'm doing is that I will just pass the reference of the original array and just indicate the size of the array that I'm working on based on an integer variable. So just size is going to, this variable size is going to tell me that how big is the part of the array that I'm working on. When I'm calling it originally, I would pass, for example, if the size of the array is, for example, 1000, you will pass, for example, search that array that you have, let's just call it a 1000, and that value, that specific value that you have. Okay, so now let's look at the definition that I wrote. Until the size is greater than 0, it means that there is still something to search. Okay, so until the size is greater than 0, it means that the size of the problem is greater than 0. There is still something to look at. So what you are looking is, you are going to look at the last item, right? Where is the last item? The last item is going to be, if you have, for example, n items, that's going to be at index n minus 1, right? So I'm checking array index size minus 1 and compare it to x. If it is equal, return true. If it is not equal, you wanted to recursively call the same search function, right? So you recursively call the same function. This is again the same search method, passing the same array reference so that I don't need to copy the array. But what I'm going to reduce is reduce the size of the array. So be careful when I'm saying reducing the size of the array, the actual size of the array is not changing. This AR is going to be of the original size. But what I'm changing is that that variable size will be reduced So it's just like I'm simulating that I'm working on, a part of the array. For example, from index 0 to index 998, okay, until this index or something, and passing the same variable x. So whatever the result of this one will be returned. If it is true, the true will be returned. So it is x is in the array somewhere else. Or if it is false, it will be returned false. You can see that if this one is not going to happen, and okay, let me see. If the size of the array is not greater than 0, what does that mean? It means that the size of the array is going to be 0, right? What does the size 0 is going to mean? The size 0 means that you have searched for everything. It is exactly the base case of your search, the base case of your recursion. When the size reaches to 0, this is going to be the base case. And so the base case for the search is going to be clear. If the size of the array is empty, if the size of the array is 0, if the array is empty, definitely the item x that you are looking for is not going to be in an empty list, right? So the base is going to always be false. Okay, so let me actually just, for example, run this recursive search over this example that I have here. Just assume that you are looking for, for example, you are looking for 5. The value of x is 5, right? Size originally will be 0, 1, 2, 3, 4, 5, 6, 7. So the size originally is going to be 10, and you will actually search for, so it's just like you call your function, just assume that, let's just call it s. You pass your array, size 10, and the value 5 that you are looking for. Okay, so if I actually check the this recursive method that I wrote here, you check the value of size. If it is greater than 0, you will check array index size -1 with x. So array index size -1 is 4, so size is 10, okay? Size -1 is going to be this index 9. You will compare it, it is not equal. So what you are going to do is you are calling the method search, passing the array size -1 and the same x. So here you are actually calling the same function, array size 9, and you are looking for 5. Okay, so again, it's just like here in this function call, the part of the array that you are looking is going to be this part, right? Again, what you are doing is that you compare the size with 0. It is greater than 0, so you check the last index. This is going to be its size -1. Size is 9, so the size -1 is going to be index 8. Index 8 comparing to 5, it is not equal, so you will call this recursive call. You will call the method search with size -1 and 5. So it's just called, this one is going to call the same method, a, and size 8, and you are looking for 5. Here again, you compare the size is not equal to, size is greater than 0, so you compare array index size -1 with x. Size is 8, so size -1 is going to be index 7. So you can see that this active part of the array is going to be this part until here. So you are looking for index 7, it's not equal to 5. You are going to this part. You will search, you call the search method recursively, passing the same array, reduce the size, and passing 5. So it's just like you call search, the same array, reduce the size, and you're looking for 5. Okay, so it's just like that part of the array, the active part of the array that you are looking for. is going to be this part of the array. The size is greater than 0, right? And then you look at array, you look at the last index, right? Array index size -1. So size is 7, size -1 is going to be index 6. Why did I wrote 9? Size 6. Okay, so this is going to be equal to x. What would happen here is that you return true. So here it will stop, it returns true, and then true will be returned here, and then it will be returned here, and at the end it will be returned here. Okay, so you can actually just try to search for an item like, for example, when x is equal to 15, which this is an item which doesn't exist in the list. Try to actually execute that, and you will see that this, execution of function calls will go until the size is going to be 0. And then, so when the size is 0, it's going to be the base case. It actually just returned false, and the false will be returned. Okay, now we actually come to the interesting part. We would like to know that what is the time complexity of this recursive version. We have seen the time complexity of the iterative version. Remember, it was the iterative version. We had a loop, basically, that loop explicitly go over all the indexes until it finds it, or until it reaches to the end of the indexes, and it just returns false at the end. So now we wanted to know that what would happen in the case of the recursive version. What is going to be the time complexity of the recursive version? Let me just do a little bit clean up here. Okay. So as you can see, in the recursive version, we don't have any loop. If you look at this function, this is going to be some comparison here, another comparison here. Either we are going to return true here, return here, or you have actually just some returning as well. But the thing is, what you have here is going to be a function call. So this is going to be just like a black box for you, that you don't know how much this one is going to take. You just know that, for example, you just have a couple of comparisons, right, and some returns. So if you exclude this part, this function call, everything else in this function, the body of this function is going to be done in constant amount of work, right? But the point is that you have a function call here that this one is going to take some time, and I don't know how much time this one is going to take. Okay, so before I give you, the formal way to analyze the recursive methods, I'm going to just give you the idea that's, what's happening here. You can see that although the recursive version does not have this explicit loop that we had it in the iterative version, but when you are executing, what would happen is that the computer will create these function calls, all of these function calls, right? If the item exists in the list, for example, if it is at index 5, that's index 4. So how many function calls you would have? When it was at index 6, it actually had n minus 6, the total number of actually, n minus 6. If the item is at index 6, the total number of function calls was going to be n minus 6. So in total, you can say that the total number of function calls is going to depend on which index the item exists, the item actually is in. If the item does not exist, the number of actually function call is going to be n, right? So because it actually goes down until it looks at index 0, and it actually even check that and then return false. So anyway, the number of function calls is going to depend on the number of items in the array. And for each function call, I can say that, okay, for each function call, except calling the function call, the rest of the cost is going to be constant, right? How many function calls you would need in general, on average, for example, it's going to be, let's just call this one theta instead of O. The total number of function calls is going to depend on n, right? So it's going to be either n or n minus 1, n minus 2. So on average, I can see that the number of function calls is going to be n divided by 2. So n divided by 2 multiplied by cost of each function call, which is going to be constant. So in total, I can say that, yes, this recursive function, although it doesn't have explicit loop, it is going to execute in theta of n, because on average this is going to have n divided by 2 number of function calls, and each function call is going to have a couple of if statements, right, and return statements. So this is going to be constant multiplied by n divided by 2 function calls. So in total it's going to be theta of n. This is going to be a linear function. So this is the idea, but I'm going to give you some, mathematical approach that helps you a lot when you are writing your future actually code. So you need to have both, vision, how to actually just, discuss about the time complexity in this way, just thinking about the number of function calls and how the function will be executed, or just writing it down in a mathematical way, the way that I'm actually just going to write it here for you. Okay, so what I'm going to do here is I am going to just write down a time function for this recursive approach. Remember when we previously had a regular code, we write a time function for that, right? So let me actually just do it here for this recursive, for this non-recursive search. Let me write the time function for this one. Okay, here the time function that you wrote was, for example, you would say that I am going to have, an initialization here, comparisons that I should know that how many times this comparison will be executed, and this increment. So this is going to be 1 initialization plus 2 multiplied by n, which n is going to be the number of iterations, right, because of this and this one. And then you have an if statement here. This is going to be, again, be executed the number of iterations that you have, and this one will be executed only once. This one will be executed, if it executes, it will be executed only once as well. So again, the number of comparisons here is going to be n. Okay, where n here, let's actually just, instead of n, write it down as k, because I wanted to actually use n for the size of the array. So k number of iterations. Okay, so in total this is going to be something like 2 plus 3k. This is going to be the time function, right? What is the value of k? The value of k is going to be the number of iterations. The number of iteration is going to be different depending on the value that you are searching. But on average, I can say that k will be n divided by 2, where n is the size of the array. Okay, so I can say that for the time function that I have, f of n is going to be 2 multiplied by 3 n divided by 2, something like this. And from this, I would conclude that this is going to be, you know, some constant multiplied by n. So this is linear. In total, at the end, I can say that this is going to be theta of n. So it was clear how to write the function, time function, for this non-recursive approach. I am going to show you that how can I write a time function for this recursive approach. Okay, so instead of f, let's me actually just, because I'm using the notation t, let me just write it as t. So this t of n is going to be the time function. That's just like that f of n that I explained previously. T of n is going to be the time that would take for this function to be executed. What is the n? N is going to be the size of the problem, which is going to be the size of the array. Okay, here it's not going to be the exact size of the array. This will be actually emphasized, it will be indicated by the size, because I have exactly a variable that I'm passing and saying that which part of the array I'm working on. Okay, so n is going to be the size of that part of the array that I'm working on. So at the first, when you are calling this function, search with array, and whatever is the size of the array, that size is going to be n, right? And x. I wanted to know that how much time this function is going to take. That will be indicated by t of n. I would like to actually find this relation, this function. So what I'm doing is that I will just evaluate and check that what I have in the definition of this function. I have an if statement here. So one evaluation, this is going to be a simple comparison. So one comparison, one instruction here. Let me actually use a different color. So one comparison here. I have one comparison as well here. I have either a return statement here, or I have a return statement here. So one more actually a statement. But the thing is, this returning is going to be involved in calculating something. What is that? This is a function call. So I don't know, this is going to be 1, 2, n power 2. What is going to be the number of instructions which is required by this function? This is a function call, and I don't know how much time this one is going to take. But I know something. I know that the function that has been called is exactly the same function as I am actually looking at, and I would like to find the time function for that. But there is a difference here. The time that would exist, so just assume that the size is going to be n, right? The size is going to be n. So if I assume that the time that would take for searching with size n is going to be tn, this is something that I'm looking for, okay? I don't know what is this, but I can say that I am calling it t of n. So if I am calling the same function, but with a smaller size, I can give it a name, right? And say that the amount of time that would need this function to be executed, is t of n minus 1, right? So whatever this one is going to be a function of n, right? This is going to be exactly the same, but the difference is that of the smaller size, right? How much smaller? By minus 1 smaller. This is clearly indicating that this is going to be reducing the size by minus 1. So I can say that this black box that I don't know how much time it's going to take, but I can give it a name and say that, okay, this is going to be t of n minus 1. So at the end, for t of n, I can write down a relation. What is that? That's going to be the summation of everything that's happening here. This one comparison here, a statement here, and one statement here. So in total, it's going to be a constant number of statements, right? A constant number of instructions. So I can say that t of n is going to be some constant number of instructions plus, so it doesn't matter if it is 3, 4, whatever, this is going to be constant, right? And it's just because of these if statements that I have here and the return values. So constant amount of instructions plus t of n minus 1. So what I got here is a recursive relation, right? Again, I got a recursive relation for the time function. Obviously, if you have a recursive function, if you have a recursive method to investigate, if you are looking for the time function for that, the time function will be definitely recursive as well. Now what I can do is that I wanted to solve this recursive relation. So how can I solve this recursive relation? Let me actually just add it, I added a slide here. Let me see that. How can I add an empty? Okay, let's just duplicate this and then remove this. Okay, so what I had from before, what I actually got here was this recursive relation, right? I'm going to just write it down here and solve it for you. The recursive relation that I have is t of n is equal to some constant plus t of n minus 1. Okay. So not only I need this recursive relation, I need actually something else. What is the t of 0 when the size of the problem is 0? This is going to be clear again from the definition of your function, your recursive function. The definition of recursive function tells me that if the size of the array is 0, it actually directly comes here and returns false, right? So the other part is that if you pass an array of size 0 to this search, the amount of time is going to be constant. So I can just say that this is going to be constant amount of work. If you don't have any item in the array, if the array is of size 0, how much time it would take? It would take constant amount of time, right? So I need to add this one to my recursion as well. Whenever you have a recursive relation, you need to have a base case for that. So even for the time function, I need to know that how much time it would take to solve the problem if the size of the problem is 0. Okay? So I have this base case and I have this recursion. I wanted to know that what is going to be t of n. At the end, I would like to know t of n just like the way that I have executed and find t of n here, right? This was, in fact, this f of n that I would better write it as t of n. Okay, so this is going to be t of n. I found something in terms of n, so at the end I could actually conclude that's going to be theta of n, okay, or O of n. So I am going to find this t of n. How can I find this? I don't know what is going to be t of n minus 1, right? But I know something. I know that t of n minus 1 is going to be something of the same type as t of n, right? So the same recursive relation is going to be applied. So I can just say that t of n minus 1 is going to follow the same formula, right? So it's going to be c plus t of n minus 1 minus 1, right? So you can see that this is whatever I have here. You have n here, and then you had n minus 1 here, right? You had n minus 1 here, so you have n minus 1 minus 1. So it's just like t of n is going, t of n minus 1 is going to be c plus t of n minus 2. Okay, what I'm going to do is just to take this one and replace it here, so that from t of n, I'm going to actually just simplify t of n and reach to c plus t plus t of n minus 2. Okay, so what I did here is that you might actually just say that, okay, still I have some that term t here. That's fine, but the thing is I made t of n minus, this recursion part smaller. And the whole point is that I'm going to make it smaller and smaller until I reach to t of 0, so that I can actually just replace it with some constant, because I know what is the answer for that. So I would just repeatedly substitute this t of n minus 2 and actually just make it smaller and smaller until I actually reach to t of 0 and just put this one. So if I replaced it one more time, so this t of n became c plus t of n minus 3. Why did I have 3 comparisons? Okay, so if I again replace it, I would get something like c plus t of n minus 4. Okay, now you can actually see that I am decreasing this size each time by 1, and I am adding one more number of these actually terms of c each time that I'm actually decreasing. So what you do is that you keep just decreasing the size of n on the right side, and at the end you would have a couple of c's. Let me actually just remove all of these brackets. Until t of 0. Okay, that this one will be replaced by another c as well. So in total, how many number of c's you are going to have here? How many number? At first you started from n minus 1, then you actually reach to n minus 2. By just decreasing n by 1 each time, you are adding one term of c. So in total, the number of c's are going to be n. So n number of c's are going to be here. And yeah, you actually just simplify t of n. T of n is going to be cn. Okay, that's good. Now I can actually just conclude that this is going to be theta of n, because that c is going to be some constant. I don't care that if it is 4, 10, 1, that's going to be some constant amount of work, right? At the end, the total time complexity is going to be theta of n, sorry. So this is the, the way that we can, the mathematical way to prove that what is the time complexity of some recursive method. I have actually written all those approach that I have done in this slide here for you as well. You can just read that through that. Okay, before I finish this video, I would like to basically have a look at the binary search as well. Whenever we talk about the sequential search, it's always actually nice to mention and talk about the binary search as well. If you have a list of items, a list of random items, you cannot do anything better than sequential search, because if you don't have any information about the order of the items, or if you just know that the order of items is going to be completely random, so you don't have any information about that, you have to look for the item, look at all the items inside the array one by one. So that's going to be sequential search, and sequential search is going to be linear time. But what if we know that the items in the array are comparable to each other and they are going to be sorted? For example, just assume that I have an integer list of items and all of them are sorted in increasing order. So using this information, I can conduct a much faster search, which is going to be actually binary search. The whole idea of the binary search is that if I have an array of items which are sorted and I'm looking for some specific item X, what can I do is that I can look at the middle index among all the items that I have and just compare X to that. If X is equal to that item, so I'm lucky I found it. If X is not equal to the item at the middle index, so let's actually just call that mid. If array index mid is not equal to X, there is going to be two options, right? X is going to be either greater than mid or a mid index, or it is going to be less than the mid index. If it is greater than the mid index, X should be, if X exists in the list, it should be, if it is greater, X should be here, right? Definitely, because the items are sorted, X cannot be on the first half of the array. So if you are looking for this X, you should actually look for the X in the the larger side, on the right side of the mid index. But if X is smaller, you have to look for the value of X here, because X is smaller than the value at the middle index, and if X exists in the array, it should be in the first half. Okay, so this is, you can actually see that this is exactly the definition of a recursive approach, right? I'm telling you to look at the middle index. If X is equal to that, okay, just return true. So it's just like you have these three cases. If X is equal to array index mid, just return true. If X is greater than array index mid, just search for, let's just call this one binary search, and you are passing array, for example, and that's going to be for an X. So what you need to actually do is to return binary search, sorry, not search, binary search. So first half, let me actually just show it using the syntax of Python here. Then later on I'm going to show you the Java code and the trick. So this is going to be, for example, until the index mid. So it just actually shows you that the first half from index 0 to index mid and searching for x, and else. So just call this one another else if, and else just search for it. Binary search on the second half, that's going to be from the mid index plus 1. So it's just like from this index to the end, and the value of x. Okay, so you can see that this is exactly the recursion. You are actually calling the same function over the first half or over the second half. Okay, so here is the code that I wrote in Java, and I'm actually showing you the trick that I have done here. I would like to write down my code so that I do not create, some sub arrays each time that I'm calling the recursive function, because of the, avoiding the overhead. This is a very important trick that you should learn, and whenever you are writing your code, it is always good that it doesn't matter which programming languages you are using. It's always good to do this coding practice, that try to avoid recreating the arrays again and again and again. Instead of that, if you are working on an array, it's better that you just pass the reference of the array, and if you are working on some part of the array each time, just indicate that using some indexes. Okay, just like in the previous code that I wrote for the sequential search, that I passed one variable that shows the end of the array, because always the beginning of the array was 0. Here I'm going to use two variables instead of just one, because, for example, sometimes at the beginning you would actually start it and say that the beginning of the array is going to be here, the end of the array is here. But at some point you might wanted to say that, okay, the beginning of the array is here, the end of the array is here, right? When you're actually working on the second half. So the beginning and end might be actually variable, both of them. That's why I am using two variables to indicate the start and end. Okay, so in this way, I do not need to copy the array and create some new sub-arrays. I'm just changing the value of a start and start and end will actually just indicate which part of the array I am working on. So originally, when you are calling your binary search, and you have an array of size n minus n, for example, the size of your array is n, you would call something like this. Binary search your array, whatever the name of that is. A start is going to be index 0, and end is going to be index n minus 1, and the value x that you are, for example, looking for, whatever is x. Okay, so you would call your binary search using these initial values. The name of the array, a start will be 0, and the last index is going to be n minus 1. Okay, so let me actually just show you that how we find the middle index, how we preserve the base case, when we stop, when we are searching in the first half, in the second half. The first thing is that in your function, you need to find the middle index. What is going to be the middle index in your array? Be careful. At the beginning, the middle index is going to be index, for example, n divided by 2. But the size of the array that you are working on is changing. So, for example, when you are working on this part of the array, the middle index is going to be somewhere here, right? So where to find that index? That index is going to be whatever is a start plus the end, the last index, start plus n divided by 2 is going to give you this proper mid index. So I'm going to use this formula. This is very important. Okay, the mid index is going to be whatever is a start, because we don't know which part of the array we are working on, plus n divided by 2. So it properly actually tells me that this is going to be mid. So, or for example, if I had at a situation that this was a start, and this was, for example, end. So a start plus n divided by 2, it actually gives you the mid index properly. Okay, so this formula is important. Instead of actually just write it as n divided by 2, n divided by 2 would work only once. So in the later call of the function, the mid index is going to be changed based on what is a start and what is end. So mid, just forget about this line. I'm going to come back to that later. So you calculate the mid index by the value of a start plus the value of end divided by 2. So this is going to be the mid. The rest of that is going to be easy. You compare array within at index mid with x. If it is equal, return true. Okay, so this part is easy. After that, you are actually just checking that if array index mid is smaller than x, this is the case that this is not equal to x. If it is not equal to x, it should be either smaller than it should be either greater, x should be either greater than the middle index, or it should be smaller, right? If it is greater, you are going to search for the inside the, for example, just assume that you have this case. If x is greater, you wanted to actually search here, right? On the larger side. So you are calling the same binary search, the same function. You are passing the name of the array. What is going to be the starting point here? The starting point is going to be exactly the index after the mid, right? Because you are going to start from after the mid. X is not in the mid index, right? You should start from one index after the mid to the end. So what I'm passing as the start, so this is going to be the new start. Okay, you are passing this value as the start and the previous value of end. So end hasn't been changed, end is still here. Okay, but if you are looking at the smaller size, what if the value of x is smaller than mid? So you should look for at this side, right? So here the value of a start is just like before, but the value of end is changing. So you are calling the same function, passing the name of the reference of the array. The start is the same as the start, but the end is going to be mid minus 1. Okay, be careful. This is going to be the index before the mid. So whatever is mid, you should pass mid minus 1. Okay, so this is the full array except that this first line that I skipped at the beginning. What does this line actually say? This line is actually catching the base case. What is the base case in the binary search? Just like sequential search, the base case is that when the size of the array became 0. When the size of the array became 0. Size of the array is 0. Just write it as that. So when the size of the array, the original size of the array, it actually can be anything, right? But you are making the array smaller and smaller. You are just saying that, okay, look at the full array, then look at, for example, the first half, or look at the second half, and then again make it smaller, and smaller. So you are changing the size of the array by changing the value of a start and end. You can see that either you are increasing the start or you are decreasing the end. So it's just like the value of a start, so if it is the original array that you have, a start will be here. I'm going to actually just show it as S, and end will be here. Okay, and then in the next step, either you are updating S and actually just updating S to this one. So it's just like either S is moving forward or E will moving backward. So at which point, so when you actually S is, let me actually just say it in this way. When S is actually indicating at index 0, referring to index 0, and E is referring to index n minus 1, the size of the array that you are working on is going to be n, right? So when S became, for example, this is going to be the mid index, mid, and this is going to be, for example, S is updated. If S is updated to mid plus 1 and E is here, the size of the array became n divided by 2, right? Something like this. And then just assume that you continue and again calculate the mid, and then you search for here, and actually the E will be updated to here. The size of the array in this case will be n divided by 4. Okay, so size S and E, start and E are actually approaching to each other. Whenever S and E, S actually became greater than E, it actually tells me that the size of the array became 0, because that part that you are working on is going to be empty. So this if statement is exactly checking this condition, that whenever a start became greater than end, it means that, that part of the array that you are working on is empty. You reach to an empty array. And this is the base case, and you return false for that case. Okay, so the first line is going to be actually just capturing the first line is just capturing the base case, that when the size of the array became empty, you return false. So now what I'm looking for is the time complexity of this function. So what is going to be the time complexity of binary search? I'm sure that you know the time complexity of binary search from COMP251. It has been discussed there, right? But I would like to give you the proper investigation of the time complexity for this function here. We are going to do exactly the same process that we did for the sequential search, that to actually check what is going to be the time complexity of this function. Let me actually just completely erase this part as well. Okay, so again, the thing is that we are looking for T of n. Okay, this is our question. What is n? Just assume that when I am calling the function originally, I would call it in this way, right? Binary search by passing the name of the array, a start point is 0, end point is -1. Okay, so the start point and end point are basically telling me the size of the array, the original size of the array. If I haven't actually searched for anything yet at the beginning, I'm looking at the full array, right? It is just like at this point that the start point is 0, the end point is n-1. And what is the size of the array that I'm looking for? The size of the array that I'm searching is going to be n. Okay, so this is exactly that T of n. This is exactly that Tn that I have. Exactly that n that I have in that time function T. Okay, so now I wanted to actually just check what I have inside this function, function that I have written. I have some comparison here. I have some addition, division, and assignment. Okay, so I'm just actually looking at them as some constant amount of work, right? And then you have some comparison here. You can either actually return true here, or maybe this is going to be false, then you will come to check this comparison as well. Okay, so ignoring, except this function calls, the rest of the function is going to be just some constant amount of work, right? I'm going to say that this is going to be some C, some constant amount of work. So far for T of n, I have some C, but it's just because I have skipped these two black boxes. I have one black box here, I have one black box here. What are these black boxes? I have a function call of the same function, right, but different size. So again, I'm going to use this term t, the function t, but I wanted to know that what is the size here? What is the size of the function that I'm actually, what is the size of the input that I'm working on? You can see that this part is talking about the changing the start to this index mid plus 1. Okay, so the start is going to refer to this mid plus 1. So the start is going to be updated to this one. So if I am working on this part of the array, how much is the size of the array? If the original size was n, this size is going to be n divided by 2, right? Okay, so I can replace this question mark with n divided by 2. Okay, wait there. I'm going to actually just investigate that what is going to be the cost of this one. Again, here I have another function call. This is going to be the same function again. So I can use the same term t, and I don't know what is going to be the size of the problem that I'm solving here. But by looking at the argument, it tells me that it's just like you are updating end to refer to this part, mid minus 1, which basically tells me that I am solving the same problem, searching for an item on this part of the array. What is the size here? Although this is the first half, but in terms of the size, it is exactly like the previous size, the previous half. This is going to be n divided by 2. Almost n divided by 2, but they are not going to be the exact number. I'm not really care about that. For example, ceiling of n divided by 2, floor of n divided by 2, whatever. Anyway, it's going to be something around n divided by 2. Just don't be very picky about this. So again, here I can actually remove this question mark and say that this is going to be a problem of size divided by 2, n divided by 2. Okay, so what should I write here? Does t of n going to be equal to some c plus? So am I calling this one, or am I calling this one, or both? So if you look at the definition of the function, you are comparing x to the middle item. So it is either going to be greater than the middle item or less. So it's not possible to calculate both of these two function calls. You are going to be either executing this line or executing this line. So just one of them. But the good thing is that both of them are equal. So I can say that, okay, just one of these are going to be executed. How much time it's going to take? This is going to be t of n divided by 2. Okay, so I'm done. I found that recursive relation for the time function. So you can actually, if you look back at this recursive function that I found here, it was t of n equal to c plus t of n minus 1. In the binary search, instead of having n minus 1, I make the problem much smaller. The size of that was going to be n divided by 2. So you see the difference between these two recursive relation. Okay, this is actually the one that I wrote. Okay. So before I go and solve this, because at the end you wanted to know the exact value of t of n in terms of some theta of n, right? You wanted to actually solve this. So at the end we need to solve this recursive relation. So I need to also know what is going to be the base. So the base is this line, right? The base is telling me that when the size of the problem is 0, when there is nothing else in the array remain to search, t of 0 is going to be constant, right? Okay, this is going to be again that base case for me, which is similar to the sequential search. This is, if you reach to the size 0, it's going to take constant amount of work. So what I'm going to do here is I'm going to solve the recursive relation for you. So it actually just tells you that this is the recursive relation that I got, including this part that the base case, it's going to be C. So just constant amount of work for the base case. So I'm going to solve this equation here. Okay, so I don't, unfortunately, I don't know how to create a new slide here, but anyway, I am going to delete this. Okay, delete this, that's enough. Okay. So let's just move here, this here, and here. This is something that I'm going to actually work on. I'm going to solve this recursive relation and at the end tell you that what is t of n in terms of theta. What is going to be the time complexity of the recursive relation. What I'm going to do here is, again, I'm going to actually just substitute this t of n divided by 2 and make it smaller and smaller inside the parentheses so that I reach to the base case and I can replace it with actually c. So I'm going to actually just do the same process, just substituting and make it, that value is smaller until I can actually just replace it with the known value of the base. So t of n is equal to c plus t of n divided by 2, right? So instead of t of n divided by 2, what can I write? We can see that whatever is, because t of n is equal to t of n divided by 2, so t of n divided by 2 will be equal to c plus t of n divided by 2 divided by 2. So it's just like this is going to be t of n divided by 4. Okay, this is very important that you know I'm replacing n with n divided by 2. So wherever you see n, you should replace it with n divided by 2. So it's just like this n will be replaced with n divided by 2. So another division should be applied. So in total, I would get n divided by 4. So what I'm going to replace here after one step of the replacement is c plus t of n divided by 4. Okay, so now you can see that I got two terms of c and I make this one as smaller as t of n divided by 4. Just apply the replacement one more time. If I apply the replacement one more time, you can see that this t of n divided by 4 can be replaced with c plus t of n divided by 8, right? Because n divided by 4 divided by 2, it's going to be n divided by 8. So the result here is going to be c plus C plus C plus T of n divided by 8. So now I wanted you to see this pattern, that I replaced n, I mean this T of n, twice, and what I got is, you can see that so far I have 3 terms of C. So I got this formula after 3 times. This is very important for me, this formula. 3C, right? 1 here, 1 here, and 1 here. And what I got here is T of n divided by 2 power 3, right? 8 is actually 2 power 3. And this formula was correct for this one as well. This was equal to 2C plus T of n divided by 2 power 2. Right? 4 was 2 power 2. I'm actually just going to tell you that if you keep replacing this for one more step, this is going to be 4C plus T of n divided by 2 power 4. So it's actually just going to give me a nice actually approach. How much I'm going to actually continue this replacement, just assume that I'm going to continue until I reach to this point that I don't know how many times, but as many number of times that you continue, let's just call it K, for example. K number of C plus T divided by n, sorry, T of n divided by 2 power K. So when you are going to stop, when the size is going to reach to 0. When is that? So it's just like when 2 power K became greater than n. Okay. So let's just actually just put it one step back. So it's just like you started from 2, then make it 4, then make it 8, 16, and you are actually just approaching, you are going up until this 2 power K became greater than n. So basically what you are doing is that, let's just actually just simplify it in this way, that until n is equal to 2 power K, what is going to be the value of K in that case? The value of K is going to be log of n. So it's just like you apply the log over n and apply the log over this 2 power K. So K will be log of n. So whenever K became greater than log of n, this part became 0, right? Because the 2 power K, this is an integer division. So when 2 power K became greater than n, it's just like K became log of n plus 1. So when will you stop? When K is equal to log of n plus 1. So this is the value that you stop. Okay, so when you reach to that part, this part became 0, and this is going to be replaced with C, with another C. So what is going to be the total result of T of n? T of n is going to be something like K plus 1 C. And what is the value of K? The value of K is based on n, right? This is going to be log of n plus 1. So in total, I can say that it's going to be log of n multiplied by some constant. Let's just call it C. And it is going to be C, log of n multiplied by C plus some other actually constant, which is going to be ignorable, right? So what is going to be the the theta of t of n. So theta of n will be some constant of log of n multiplied by log of n. So t of n is going to be theta of log of n. That constant is going to be ignored at the end. So that's it. That's why binary search is going to be, the time complexity of binary search is going to be log of n. Much faster than the linear search, right? We solved the linear search. That recursive relation is going to give me this t of n equal to t of n minus 1 plus c. This is going to be theta of n, unlike this recursive relation that I just solved here, and I got theta of log of n. And I believe the idea is quite clear. If you look at the recursive relations, here in the binary search, you are making the problem much smaller. It's just like each time you are making the problem half of the previous size. N would become n divided by 2. The next time it would become n divided by 4. So you exponentially decreasing the size. That's why the time complexity is going to be logarithmic. Okay, that's why it's going to be much faster, because you are decreasing the size of problem much faster than just decreasing it by 1, sequentially decreasing it by 1. So this is the time complexity of, this is just a discussion about the time complexity of the binary search, which is going to be theta of log of n. Okay, I'm going to stop and I'm going to finish the video here. I will talk about the rest of, I'm going to just discuss and look back at the Fibonacci function. That was something very interesting. So in the next video, I'm going to just discuss the Fibonacci and probably solve more examples about recursion and how to get the time complexity of the recursive functions.